Good morning and welcome back to Classical Mechanics 1 CMI. This is lecture 8 on 19th October 2021. So we have 33 participants. What about the previous lecture? Has it ended?
Yes, sir. I think it ended.
Okay, fine. Yeah. So while we get started, we've had you submit the third assignment as well. That's very good. Please do remember to hit the submit button and not leave things as drafts, because this has happened a few times. And I will probably spend a little bit of time mentioning a few things about the about problem set 2. Yeah. Meanwhile, are there any questions in general? Okay. Yeah. So perhaps I will share my screen. Okay, a few clarifications on problem set 2. We will talk about them again. I mean, other things later as well. Yeah, let's make sure.
Repeat what is said right now.
Yeah, I just said that I'm going to say a few words about problem set 2, which you submitted last week. I just want to mention a few comments about a few of the questions. Question number 3 concerned a linear change from Cartesian coordinates x and y to u, which is ax plus by, and v, which is cx plus dy. Okay, so this is called a linear change of variables or change of coordinates. Yeah, and we are told that boldface u or vector u ax plus by hat and v vector cx hat plus dy hat are vectors in directions of increasing u and v coordinates respectively. Okay, so just to so I mean, there are many examples here. You could choose specific values for a, b, c, d. I mean, the simplest one is a equal to b, a equal to d equal to 1, and b equal to c equal to 0. Now, what is that transformation? Can you identify it?
Identity.
Yeah, so this is the identity. So it just says that u is equal to x and v equal to y, does nothing. You could also do scalings. The scaling would be something like u is equal to 2x and v equal to, let us say, 3y. Yeah, so this is a rescaling of your coordinates, where in that case a and d are given by 2 and 3, while c and b are both 0. You could do other things. You could rotate your coordinates, in which case by some angle. So there are many examples. So for example, in a rotation, your xy coordinate system would look like this: the xy axis, and the uv axis, suppose you did a counterclockwise rotation by some acute angle, you would go to u and v in this manner, by some angle theta, for instance. So there are, you can cook up a lot of examples by choosing appropriate values for a, b, c, d. Now, the specific question that was asked is, how do you guarantee that u and v are orthonormal vectors? Yeah, that is, find conditions on a, b, c, d such that u vector and v vector are orthonormal. Yeah, so that is, going by definitions, orthonormal means orthogonal and of unit norm. Okay, so orthogonal means u dot v has to be 0. Yeah, and automatically, of course, v dot u would also be 0. Yeah, because it's commutative. So imposing this condition, what do we get? If I take u dot v, I'm going to get ax hat plus by hat dotted with cx hat plus dy hat. So bear with me if this is something you have done and are completely familiar with. So the answer here is ac plus bd. Yeah. Now, normal means u dot u equal to 1 and v dot v equal to 1. Okay, you want to impose both these conditions. Now, u dot u equal to 1 is the condition that a squared plus b squared is equal to 1. Yeah, because u is ax hat plus by hat. V dot v equal to 1 is the condition c squared plus d squared equal to 1. Okay, so orthonormality is a set of 3 conditions. Yes.
Orthonormality is directly equivalent to like cross product bin 1. Oh, not exactly. Okay.
No, I don't think that is. Yeah, these are 3 conditions. The cross product being 1, I don't think it is sufficient. It's not the same. Please check that. Yeah.
But I think the dot product is 0 and the cross product is 1. Both are jointly equivalent to orthonormality.
Okay.
Dot product is 0 and cross product is 1.
Okay, you can you can reformulate this in terms of cross product, but yeah, you need
a nice Hamiltonian cross product. That's why I was pointing the cross product.
Okay. All right. So yeah, it's possible. I mean, this is the very definition. Now, it may be possible to replace one of these conditions by something else involving cross product. If you can justify it, that is fine. But at the end of the day, you need these 3 conditions. Now, the question was to interpret. By the way, who was speaking?
Vijay and Rai.
Vijay and Rai. Okay, fine. Yeah. We'll be happy to rewrite these things in terms of cross products. But for now, I just want to work with definitions. So now we want to interpret in terms of the matrix A, B, C, D. Okay, so this is anticipating some things that we will study later on. You will study also in other courses, but it's just a little observation at this stage. What does this mean in terms of this these conditions? So first of all, it is saying let's take u dot u equal to 1. Yeah, this condition. This condition says that the first row is a unit vector. Okay, Do you see that? AB forms the first row, and it is simply saying that the first row is a unit vector. Second one, v dot v equal to 1, says that the second row is a unit vector. Okay, I'm simply reinterpreting what we've written in terms of the matrix. And finally, the dot product being 0, that is u dot v being 0, that says that the first row, regarded as a vector, is perpendicular to the second row. Okay, that is a dot c plus b dot d equal to 0. So that is the statement. The first row is orthogonal to the second row. All right. So the condition that UV be an orthonormal system can be reformulated in terms of the matrix, and it is the statement that the rows of the matrix are orthonormal vectors. Yeah, so that is the statement. We can reinterpret this in another way as well. But any question about how I arrived at these conclusions? Now, one piece of terminology: a matrix whose rows are orthogonal to each other and of unit norm, that is, whose rows are orthonormal. A matrix whose rows are orthonormal vectors is called an orthogonal matrix. Yeah, I mean, this is a conventional terminology. Sadly,
Sir, what do we mean by first row is perpendicular to second row of the matrix?
So the first row of the matrix, is the row vector AB. I mean, it's the vector whose components are A and B. Second row is the vector CD. All right. So just think of them as a pair of vectors with these components.
Okay, so sir, they are dot product. I mean,
And they're dot
we
product,
just-
exactly.
okay.
Yeah. So when I say orthogonal, I mean dot product 0. Any other question about this terminology? So the terminology is that a matrix whose rows are orthonormal, that is, dot product of distinct rows is 0, and the dot product of a row with itself is 1, is called an orthogonal matrix. Yeah, strictly speaking, it should have been called an orthonormal matrix, but sadly, the terminology is orthogonal matrix. So we have to stick to that. Now that condition, so this is all that was being asked in the question. There are ways to write this in even more neat ways. I will leave it as an exercise to you. So if I call this matrix capital M, this matrix M, then I invite you to verify that M times M transpose is the identity matrix, that is 1, 0, 0, 1. I invite you to verify, and this is not hard to do. M transpose is the matrix. Would you like to tell me what is the transpose matrix? What are the entries? What's the first row?
AC.
AC, very good. And the second row is BD. Yeah. Basically, we flip the matrix along the diagonal, the entries along the diagonal. So this is the transpose matrix. And then the original matrix, of course, was ABCD. Now, if you multiply the two, that is, I put this transpose by the side, multiply the two. Yeah, the way to multiply is that first row times first column. I'll get A squared plus B squared. Yeah. Then this entry is first row times second column. You'll get AC plus BD. Yeah. And I let you do the remaining two. And this we have observed is 1. This we have observed is 0. Yeah. So like that, you will discover that MM transpose is the identity. Okay. So this was this question number 3. Any question about how we went about it?
So I
Yes.
just wrote that the determinant would be 1 and determinant of A minus B CD would be 1. So will that be okay? Will be 0. Will that be okay?
Okay. Determinant of the matrix is 1. Fine.
And determinant of A minus B CD is 0.
A minus.
A minus B CD. I mean the first row A comma minus B and the second row C comma D.
Okay. All right. I think let me look at your answer sheet, then I will understand better. But no, I mean, if you have given an answer in terms of the matrix different from this, as long as it is correct and encodes all the 3 conditions, it is acceptable. Yeah. We'll have a look at it. Yes. If it's an equivalent condition, it is acceptable.
Okay, sir. Thank you.
Yeah. Okay. Now I want to make a few remarks about one of the other questions. I think one of the challenges is to understand what the question is asking. Once that is understood, the actual doing may not be so difficult. So in problem 4, we're talking about spherical polar coordinates. Yeah, spherical polars. And we are given formulae for r hat in terms of the Cartesian components. Yeah, plus sine theta times cosine phi x hat plus sine phi y hat, and similar formulae for theta hat and phi hat. Yeah, and we are asked to verify that r theta phi form a right-handed orthonormal system. Okay, so this involves several things. First, orthonormal means that we need to check that r hat dot r hat, that is, orthonormal means we have to check that orthogonal and unit norm. Okay, so it is easy to forget that. So we have to check that r hat dot r hat is 1, as so is theta hat dot theta hat, and so is phi hat dot phi hat. Yeah, so we have to check that all of these are equal to 1. And similarly, we need to check that the dot products of distinct vectors, namely r hat dot theta hat, or theta hat dot phi hat, or phi hat dot r hat, are all 0. Okay, so you have to check these 6 conditions to show that it's an orthonormal system. Having done that, you want to check that it's right-handed in this order, which means you have to check that r hat cross theta hat is equal to phi hat. Okay, so this would establish right-handedness. Of course, you could check that theta hat cross phi hat is r hat. That is also adequate. Or, I mean, these are cyclic permutations, or you could take phi hat cross r hat is equal to theta hat. Okay, so checking any one of these 3 will establish that it's right-handed. But it is superfluous to do all 3. You can do just one. Okay, so this was our definition of right-handed.
Sir?
And yes, please, Shubham Kumar.
So, so for checking orthogonality, we could also do r dot theta cross phi and show that it's 1 after checking that they are unit vectors.
Yes. Okay. After checking the unit vectors, you want to compute the scalar triple product, is it?
Yes, sir. Yes,
okay.
Sir.
Okay. Yes, you're right. There are ways to reformulate this. Just make sure that it is equivalent and there is no loophole in it. Yeah. Yeah. There are ways to restate these conditions. You're right. So if you have done such a thing in the homework, we will have a look and just make sure that it's equivalent. Okay, so I won't go through the calculation here because that is fairly straightforward. using the corresponding properties of x hat, y hat, and z hat. But we just need to know what is being asked. Now, any other question about this problem?
Sir, I didn't fully get why it's superfluous to all three. I'm not pretty sure why the first condition would imply the other two.
Okay. All right. Okay. So, okay, first let me just look at it geometrically. Suppose you have x, y, z here. Yeah. What we are saying is that when you cross x with y, you get z. Okay. Now I invite you to check that if that holds and you take one more cross product. Okay, let's look at this particular setup first. Yeah. So this is a right-handed system because x cross y is z. Yeah, the way I have written it. And you do notice that y cross z, if I take my right hand from y, fingers of the right hand from y to z, then the thumb points towards x. Yeah, so y cross z is equal to x. Of course, these are all hats, and x cross y equal to z. And then there's the third one. If I take z cross x, I will get y. Okay, so these are all true for this system. Now, what you're asking is a proof that if one holds, the others will hold. So this requires a little calculation. And I think in previous homework we had some formulae for repeated cross products, or if we didn't, we can do that. And you can check that. Suppose you take one of these formulae and cross it with, let us say, y. Yeah, I cross this one with y. Then you'll get x cross y on the right hand side, and on the left hand side you will get y cross z cross y. And you need to simplify that expression. And using the fact that they're orthonormal, the terms will simplify, and you should get z on the left hand side. So, so Gautam Vishwanathan, at least I'm not doing it here for you, but have I sketched for you what would be involved to show what you ask?
Yes, sir. Yeah. Yeah.
Okay.
Thank you, sir.
Yeah, sure. Okay. Okay.
Sir, isn't
yes.
it enough to just show that r cap cross theta cross is equal to phi cross, and like we don't need to show also that theta cap cross phi cap is equal to r cap?
Correct. Yeah, one will do. One will do. You're quite right. However, you cannot ignore these 6 conditions. They too must be checked.
Yes, sir. Yes.
Okay, yeah. You're quite right. Yeah, so one will do among these 3. So here all 6 needed. Yeah. Yes. Any other question?
So can we like? So can?
Yes,
that,
Ripunjay,
like,
could you repeat your question?
The transformation matrix A into A transpose is the identity matrix. So can we show that the transformation matrix, that is A multiplied by A transpose, is equal to the identity matrix, and then like based on what we derived on the previous problem for the first part for the 6 conditions?
Yeah. Okay, wait a minute. See, the previous problem concerned 2-dimensional plane and a transformation of the 2-dimensional plane, whereas in this new one we are working in a 3-dimensional space. So I can't quite use the same condition. But okay, perhaps you have something else in mind. Okay, you want to formulate. Okay, you want to encode some of these conditions through a matrix. Yeah, yes. You can do that. Yes, you can do that. You can form a matrix whose entries are the components of r hat, theta hat, phi hat, and formulate these conditions in terms of that matrix. That's right. You're quite right. Is that what you meant?
Yes, exactly.
Yes, indeed. Yeah. So that was Ripunjay. Yes, you can form a matrix A whose entries are r hat dot x hat, r hat dot y hat, r hat dot z hat. Okay, these correct me if this is not what you meant. Yeah, is this what you meant?
Yes, sir. Yes, sir. And then this is orthogonal.
Yeah, exactly. So you can form such a matrix where the entries of the first row of A are the components of the R vector or the R hat vector in the XYZ system, and so on for the second and third rows. And then you will verify that A transpose is equal to the identity matrix, like we did in the previous example, and that will encode all these 6 conditions for you. Yeah. Then this will ensure that, so there's a similar thing, phi hat dot x hat, phi hat dot y hat, and phi hat dot z hat. And this will encode the orthonormality of r, theta, and phi. Yes. Okay. Yeah. Any other question?
Sir,
Yes, Soumyadeep Paul.
so in question 4, I think of the 6 conditions, we don't need 2 conditions. Like in the dots which are 0, we need only 1 because the cross product implies that they're perpendicular.
Okay, you are suggesting that one can eliminate one of the conditions. Okay, you would need to explain to me how you would do that. But according to definitions, you do need to check all 6. I'm not seeing.
So if I do r cap dot theta cap is 0, and then I show that r cross theta is equal to 5, that implies that phi is perpendicular to both.
Okay. Look, you are replacing one of these conditions with some cross product condition. Yeah, so yes, you are welcome to do such things. Yes. So we cannot eliminate one of these altogether. You can replace it with some other condition if you like. Yes, you are welcome to do such things. Just check that it is. Is that what you meant?
Yes, sir.
Okay, yeah. So you're right. There are many ways to show that something is an orthonormal system. What I have described is the definition. You can replace some of these conditions using cross products and so on. And cross products being vectors, they actually can often be more than one condition involved. There may be 3 conditions in one vector condition. So there are ways to reformulate this. Now that was the 4th problem. Just a couple of remarks about the 5th problem. The 5th problem again involves spherical polar coordinates. Yeah, but this is concerning the trajectory of a particle. Now, and we are looking at r hat of t along a particle's trajectory. Yeah, so here is the trajectory. And at any point, okay, let me draw my coordinate axes. And this is the origin. This is the radius vector or position vector at time t, particles moving this way. And at this point, you've got the r hat vector, unit vector. And we are asked to express r hat as a linear combination. I'm sorry, the time derivative of r hat, yeah, d by dt, as a linear combination of r hat, theta hat, and phi hat. Okay, so that is not so difficult because the formulae are already given in the previous question. You're supposed to take the formula for r hat, which I wrote a little while ago, namely this formula. Yeah, this formula, and simply differentiate it in time. So you'll get minus sine theta dot z hat and so on. Yeah, you're supposed to differentiate it, get a formula for r hat dot. Now I will just write that formula, r hat dot or d by dt of r hat. If you compute it, and I think most of you have been able to do this, the answer you get is theta dot theta hat plus phi dot sine theta phi hat. Okay, so this is the formula one obtains for the time derivative of the unit vector in the r direction. Yeah, you notice that the unit vector in the r direction changes direction as you move along the trajectory, and this explains this. It describes how it changes. Any question about and the procedure is the same as what we did for plane polar coordinates. The same kind of differentiation. You do it in the spherical polar case. Any question about how one goes about doing this? Okay, now the second part of the question was to explain the absence or explain the coefficient of r dot here, r hat here. So the coefficient of r hat is 0 in this case. So we want to explain the coefficient 0 of r hat in this formula. Okay. And several of you have got it, but I do want to clarify the matter or give the reasoning why it is 0. The point is that r hat is, of course, depends on time. R hat is a unit vector. Okay. No matter where you are, r hat is a unit vector, and therefore its length can't change with time. That means d by dt of r hat dot r hat must be what? See, r hat dot r hat is the length square. So what is d by dt of r hat dot r hat?
0.
0, because the length can't change, or the square of the length cannot change. This must be 0. Well, let us work out what it means. It means that r hat dot r hat, using the Leibniz or product rule of differentiation, plus r hat dotted with r hat dot equal to 0. The two terms are the same. So I will get r hat dot dotted with r hat equal to 0. Yeah, the two cancels out. So it is saying that the r hat component of r hat dot is 0. And that is indeed what we found here. Geometrically, what is it saying? It is saying that since r hat is a unit vector, the change in r hat cannot point in the direction of r hat, because if it did point in the direction of r hat, then the vector would increase or decrease in length. Yeah. So that since r hat is a unit vector, its infinitesimal change cannot point in the direction of r hat, as that would cause a change in its length. So this is the essential point.
Sir, here in the geometrical interpretation, I have
Yes.
just mentioned that the operator, I mean the DDT, when it just acts on r hat,
Yes.
it can only rotate it and cannot change its magnitude.
Correct. Yeah, that's right. Yes, that geometric interpretation is adequate. Yeah, that would be adequate. Any question about how we went about this, or either geometric or calculus reasoning? Okay, so these were a few of the questions.
Sir,
Yes.
sir, when we do transformation of axis by rotations, like we did in the third problem.
Yes.
So then, with respect to the origin, those two coordinate axes remain same now. With respect to origin.
No, see, when we make a rotation, and if we make a rotation about the origin, then the two pairs of coordinate axes will both emanate from the common origin. So this is the picture. I mean, the first, originally x and y were along east and north direction, and u and v also emanate from the same origin. So I mean, if you were to translate things, then the origin would change. But since we are only making a rotation, I mean, this is an example. I'm not saying everything is encoded here, just an example. A rotation about the origin doesn't move the origin of the system.
So I was asking that with respect to the origin, these two coordinate axes are equivalent.
No, I would not say that. The two coordinate systems are different because the coordinate, let me take a point here, right? Okay, let me take a point here. Take a point over here. Its coordinates in the UV system, the point P, what is the first coordinate? Well, let me say it's 1, okay? What is its second coordinate?
0.
0, very good, yeah, okay. So these are the coordinates of that point because it has 0 V coordinate because it's along the U axis. On the other hand, the same point P, the address of that same point P in the XY system, so this is in the UV system, in the XY system is quite different. Yeah, because both X and Y coordinate are non-zero. It is somewhere in the first quadrant. So it may be some other value. Of course, given the angle of rotation, you can actually work out what it is. I'll let you do that. But so this is something and something else, which are neither is zero. Okay, so I would not say that the two coordinate systems are equivalent. They just have the same origin. The values of coordinates of any given point will differ in general. The only point with common values is the origin itself. It is 0, 0 in both systems.
Yeah. Thank you, sir.
Okay, you are welcome. That was Shakti Chauhan. Okay, and yeah. Okay, so let me now, I think in effect, we have also talked about, okay, there were problems 1 and 2, which by and large, I think you have all got right, but I'm happy to discuss them as well if there are questions. I mean, either this time or in the next lecture. Any question about this homework set? Yeah, if not, let me now return to our discussion of Newton's laws and the like. Last time, which was a whole week ago, we talked about the number of degrees of freedom of a system. Yeah, and I just want to recall the definition. So let me just do that. I have tried to, in the notes, I have tried to improve the presentation, make it a little bit more precise, so that some of the questions you had last time are addressed. So let me just go over one of these statements. Yeah, for a system of particles, the number of degrees of freedom is the number of real parameters, also called coordinates, needed to specify the locations of all the particles in the system, let us say at the initial instant of time. Yeah, to make things a little bit more easy and clear, we define some instant of time as the initial instant of time. Yeah, maybe morning 9 a.m. something. Yeah, and we ask how many variables, how many real parameters we need to specify to locate all the particles at that instant of time. Yeah, there is no trajectory involved. You are free to put the particles where you like, as long as it is the system that is specified. And you need to answer that question for your system. So if it's just a single particle, a point particle moving in this room, well, I can locate that particle at t equal to 0 anywhere in this room. So there are 3 degrees of freedom. So that is a nice way to think about it. In the third problem set, we have a more sophisticated system consisting of a rigid wire, and you have all tried to understand how many degrees of freedom it has.
Excuse me, sir.
Yes. Shubham Kumar.
Sir,
yes.
Sir, when we constrain a body, like the question you gave, in which there was a rod and we had to find the degree of freedom. Yeah. So we do that
just before you go ahead, I want to be a little careful with the use of the word constraint. We considered a particular body. namely a rigid wire, a little bit like this pencil, except that it had zero thickness. Yeah, I wouldn't call it a constraint yet. Yeah, the body itself is a wire, and we are studying it. But okay, having said that, please go ahead.
I mean, sir, like we constrain the motion using forces only now. Like if there's a body, it is held through electrostatic forces.
Okay. See, this is a separate question. Somebody presents you a body and a place where it's moving and asks you how many degrees of freedom it has. The answer to this question is independent of how that body is constructed, what keeps it together. All of those questions, while they are interesting physically as well as for general knowledge, they are not of any relevance to answering the question of how many degrees of freedom the system has. Yeah, whether the particles in this pen are held together by electrostatic forces or some other force is not relevant to this. We are simply told that you are given this wire and asked to determine how many translational rotational degrees of freedom it has. So I wouldn't, yes, you are right in a sense that the particles in this rod are constrained to be at fixed distances from each other, right? That is true. But that does not, that's part of the specification of my system. Yeah, that is already given to you, and you are only asked how many degrees of freedom it has. Shubham, is that of any use?
Yes, sir. So to some degree of extent, but I'll have to think about it a little bit.
Okay. Yeah, see, we need to clearly be very clear about what the system is. There may be certain forces, certain internal forces that have gone into making the body. We are not concerned with those because we are told what the body is. Yeah. I would like you to keep that in mind. Now, and there are other forces, namely external forces, which govern the motion of the body itself, which we have not talked about. Those again are not relevant to counting the number of degrees of freedom. Neither are the internal forces keeping the body together relevant, nor are the external ones. Yeah. Now, what is this?
So,
yeah.
Sir, I had another thing like related to this constraint only. Sir, it was, yes, sir. Sir, it was mentioned in the question that the rod can move only within the lecture hall. So isn't it like putting a particle in a box? So does that, because that is sort of a constraint that it can't be outside the box.
Exactly.
So,
yes.
Like, does it have any role in like?
No, see, that has a role. Yes, it can't escape through the window.
Because it can't go.
Right. Your question is well taken. The short answer, it has no relevance to the number of degrees of freedom. It does say that the particle can't escape through the door or the window and so on, but you still need 3 real parameters to locate it within the room. Yeah, of course, there are those real parameters cannot go from -infinity to infinity. They need to go from 0 to 4 meters or something, depending on the size of the room, but it is still a real parameter. So we are only counting the number of real parameters. Their ranges, while being of much interest, because we are, I mean, CMI doesn't occupy the whole of Siruseri. Yeah, we have some restrictions here. So the ranges of the coordinates will be restricted, but that doesn't change the fact that there you need 3 coordinates. Is that clear?
Yes.
Okay. Yeah. Any other question about this?
Sir?
Yes, Shakti Chauhan, yes.
Suppose there are two walls that are holding together a particle in between them. That's so that the particle can't move like through the walls. So like it can move along the plane of the walls. So then the number of degrees like will be affected or not? Like then there will be 2 degrees of freedom. That's it can move only in the plane.
Sorry. Okay, you're talking about the particle that is moving on a wall. Fine.
No, like there are two infinite walls. In between them, the particle is like fixed moving on the plane of the walls.
No, wait. Look, you have 2 walls here. Yeah. Now,
yeah.
Are you telling me the particle
very close? They are very close.
Okay, they're very close.
Yeah.
Okay.
Like only the particle can fit in.
Okay, you need to be very clear here. Okay, so okay, if you say only particle can fit in and the walls are so close that the particle cannot move in this horizontal direction, it can only move in the on the plane of the walls, then it has 2 degrees of freedom. If it can move in this direction, then it has 3 degrees of freedom. You have to decide how thick your walls are or how much space there is between the walls and how big your ball is. Yeah, does that answer your question? It has 2 degrees of freedom according to the way you specify things.
Yes, sir. Yes, sir.
Okay,
Thank you.
great. Yeah.
So sorry to interrupt. I have another
Yeah,
another thing
Ripunjay,
based
yes.
on what you just said.
Yeah.
Sir, is there any the way we have defined degree of freedom is by the number of coordinates or real numbers which we require to locate every point in the system. But there is another way of looking at it, like in how many directions the particle can move. Like you just said that it can move only in 2 directions, so it will have 2 degrees of freedom. So if we use the second way to specify the degree of freedom, will it be correct? Like
They will give the
completely
same
correct
answer. Yes, yes.
Yes, sir. But is it correct fundamentally? That is what I'm asking.
Yeah, I mean, after all, the number of coordinates needed, each of the coordinates gives you an independent direction in which the particle can move. So they are sort of synonymous. Yeah, it will give you the same answer. I slipped into that kind of terminology. Perhaps I should not have. If a particle is constrained to lie on this wall, which is made of my hand, well, you need 2 coordinates to specify the location on this on my palm. Yeah, you need to know along which latitude you are and along which longitude you are, roughly speaking. So that's the 2. And the manner in which I spoke is that, oh, it can move along this latitude, it can move along the latitude, longitude, and therefore there are 2. They are both the same way of counting. Is that okay?
Oh. Yes.
Okay, fine.
Sir,
You're welcome
this
to think
is,
about
like,
it again. Yeah,
like
sorry.
this system will have 2 degrees of freedom only when the origin is kept in between those walls. If the origin is outside that wall, then we will need 3 parameters to specify the location.
No, definitely not. Because see, irrespective of where you position your origin, even if I position my origin here, the distance of the origin to the wall is fixed. Yeah, the origin doesn't move. And therefore, that extra coordinate that you are talking about will not change. Namely, the distance of the wall from the origin doesn't change. So that's not something that, no matter where you are on this wall, that distance is always fixed. So it's not a free parameter. You don't need to specify it at all. It takes only one value.
Oh, yes, yes.
Okay.
It,
Yeah.
Thanks.
Okay. So any other questions on this concept? Okay. Gone. Okay. Okay. Let's go on to just a comment on this, what I call the zeroth law of classical mechanics. There was some suggestion that what I call the zeroth law is an assumption as opposed to a law. I would like to, I mean, perhaps I didn't answer that or go through it carefully enough last time. First of all, what did I say with regard to this? First of all, I said that what we would like to regard as the zeroth law of classical mechanics is the statement that the path followed by a particle in time, well, which is called its trajectory, the zeroth law states that for bodies such as tennis balls and planets and so on, that the trajectory r of t is a twice differentiable function of time. Okay? So the sense in which this is a law is that it is not an assumption, but rather an assertion. Okay, it's an assertion about natural phenomena. It is deduced by observing how tennis balls move, how planets move. It is not some self-evident fact, neither is it an assumption. For instance, it is not saying that the trajectory is a once differentiable function. Yeah, that is not what it is saying. It is not saying it's a 4 times differential function. It is requiring something rather specific. That is a twice differential function. And this could not be deduced without experimentation or plotting curves by observing motion. Yeah. And furthermore, this assertion only applies to certain bodies, like the ones I mentioned. I mean, falling bodies, like tennis balls or cricket balls, or or the moon's motion. It applies to those things. It doesn't apply to certain other things. So it is a law that applies within a certain domain of applicability. Yeah, and where it doesn't apply, we cannot use many of the concepts of Newtonian mechanics. And I gave a couple of examples, namely Brownian motion as well as motion of electrons in atoms. It simply doesn't apply. So the word law is used in a specific way in physics. It doesn't mean that it's always true. It has a domain of validity. Any law of physics has a domain of validity. In this case, the domain of validity excludes Brownian motion. It excludes atomic phenomena. It excludes nuclear phenomena. Yeah. So a law doesn't mean it holds everywhere. Just like the laws of that are enshrined in our constitution simply don't apply in neighboring countries or in other planets. Yeah. So in the same way, some laws of physics have their domain of applicability. And if you postulate that law, then you can deduce consequences. And those laws are not self-evident. They are not simply facts of logic. They are things about natural phenomena that you deduce by observing. Okay. Because it could very well have been that the trajectory of the moon is not a twice differentiable function of time. Perhaps it is something quite different. It is only by observing that we found out that it's the case. Okay, so any questions so far? All right, let me then, yeah.
By twice differentiable, what we mean?
Oh, it just means that, so R of t, okay, I mean, this is nothing specific to R of t. A function x of t is once differentiable if x of t plus delta t minus x of t by delta t as delta t goes to 0 has a finite limit for any t. Okay. Now, this is some concept which you have learned in calculus, and so this function is not once differentiable at this point. It has a sharp corner. So if the trajectory looked like this, it would not be differentiable over there. Yeah. So and why twice differentiable? Well, again, there is no, I cannot give the reason. This is what one sees by observing planets. All right. It is a law of nature. It is not something I can make up. Now, of course, it has consequences, and it is consistent with certain other laws or deductions from other laws. So, for instance, Newton's Newton's second law will involve the second derivative of position. All right, and there it will come useful. On the other hand, Newton's second law will not involve the third derivative of position. So there is no need for the third derivative to make sense. We could have trajectories where the third derivative doesn't exist. And it is not adequate for only the first derivative to exist and not the second derivative. Again, that will not be adequate to formulate Newton's second law. So yeah, I would like you to think of it that way.
So if the trajectory is twice differentiable, then that means acceleration exists.
Yeah, correct. Acceleration exists, can be defined at every instant of time. Exactly, you are quite right.
That acceleration should be greater than 0 or greater than equal to 0?
No, there is no such thing. See, first of all, acceleration is a vector. It can take any direction. It can be 0. It can be negative. I mean, even any component of acceleration can be 0. It can be negative. It can be positive. We are not asking that it have a particular value or sign. All we are asking is that it exists. That's all.
Yes,
what the value of this limit is not being, we are not constraining that. Okay. Okay, let me now proceed to what we call Newton's first law. As I mentioned, this was formulated in his famous work, the Principia, in 1687, published in 1687. So let me state Newton's first law. Newton's first law, also known as the law of inertia, says, loosely speaking, that every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by a force impressed upon it. Okay? So this is the language of a translation from the Principia. So this is not my language. Okay, so what it is saying is that everybody continues in a state of rest or in a state of uniform motion along a line. Yeah, uniform motion means its speed doesn't change with time. Speed remains constant and it remains moving along a straight line. I mean, the straight line could be pointing in any direction. Yeah. So let us restate this in symbols. In other words, the momentum, which is m times v, m times the velocity, or m times r dot of a particle that is free, yeah. When I say free, that is what was said in the previous sentence. That is, unless there is a force impressed upon it. So suppose there is no force, yeah. But let me be more precise. When I say what is it to be free, it means that it is far from physical interactions with other bodies. Okay, so a free particle is, for instance, a particle that is off in outer space. All right, that is not affected by the gravity of the Earth or other bodies to reasonable approximation would be called free. So it's very far from physical interactions with other objects. Yeah. So for such a particle, one that is free or very far from other physical bodies and their influences, the first law of Newton says that the velocity does not change with time. Because if the velocity does not change with time, r dot would be 0. So r dot would be 0. And the solution of that equation is that r is equal to r of 0 times t. Sorry.
V dot.
Sorry, I should call it something else. Yeah, I lost. So the solution of this equation is r of t is some a vector a t plus b. No, what did I do? I'm sorry. I'm sorry.
Would it be V dot?
I'm sorry. Does not change with time. So r double dot. I'm really sorry about this. Yeah. So the condition is really that r dot doesn't change with time, which means r double dot is 0. And the solution of that condition is that r is equal to at plus b for some pair of vectors a and b. So I could write that in a better way. R of t is equal to v of 0 times t plus r of 0. Okay, so this would be another way of writing. A and b are interpreted as the initial velocity and the initial location. Yeah, so this is then the equation for a straight line. Sorry about that. Okay, so basically, roughly speaking, Newton's first law says that particles that are free, in other words, not affected by other physical influences, basically either remain at rest or travel in straight lines at a constant speed. I'm sure you have heard this before. Now, there is more to this story, and that is what I intend to talk about now. We have been a bit imprecise in our statement of Newton's first law. The point is that Newton's first law, as stated, holds only in certain frames of reference. Now, I implicitly talked about a position vector r, yeah, We also talked about the velocity vector r dot and momentum vector and so on. Now, to specify such things, to specify the components of the position, velocity, and so on, we need a frame of reference. Yeah, we need an origin and coordinate axes. The question is, does this law hold in all coordinate systems or in all frames or in which frames? We have to answer that question, and we have to be a bit more precise. Okay, so the discussion that we will have right now is going to try to address this question. Now, it is found, as the examples will clarify, it is found that a particle that is not subject to any forces, that is a particle that is isolated, a free particle. Yeah. So the word a free particle, isolated body, yeah, a body far from any other interactions, body subject to no forces, all of these are synonyms. Yeah. Now, the surprising fact, yeah, is that a particle that is not subject to any forces, that is an isolated body, could fail to follow a constant velocity trajectory in certain reference frames. Okay, so we need to first understand this, and I will explain how this could happen. Yeah, so let me now try to be a bit more precise. A frame in which Newton's first law holds is said to be an inertial frame. A frame in which free particles follow straight line uniform motion trajectories is called an inertial frame. Now, let me give you an example. To a reasonable approximation, that is, if one ignores certain effects of the rotation of the Earth, then a frame that is fixed in a tennis court on the Earth, yeah, or in the cricket pitch here at CMI, is an inertial frame for the motion of cricket balls, tennis balls, rackets, and so on. What this means is that if the effects of gravity and friction are ignored, then tennis balls in such a frame would always move along a straight line uniformly. Now, this may seem obvious, but by simply changing our frame a little bit, you will see what the content of Newton's first law is. Yeah, so let me emphasize that in the next statement. It is found that Newton's first law for tennis balls, namely in the absence of gravity and friction such forces, if we ignore them, the tennis balls travel in straight lines at uniform speed, it fails to hold in a frame that is attached to a swinging pendulum or a rotating merry-go-round that is beside the tennis court. All right. Suppose you sit on a rotating pendulum and look at a cricket ball that is at rest on the pitch here. Yeah, it will not look like that ball is at rest. In fact, since I am on this swinging pendulum, it will look as though the ball itself is swinging from my viewpoint. And that is certainly not a ball that is at rest or moving in a straight line. So by this example, I hope to have demonstrated to you that a tennis ball that is free from all forces need not follow a straight line trajectory with uniform motion. It will follow a straight line trajectory only in certain frames of reference, and those frames are called inertial frames. Frames where this fails are called accelerated or non-inertial frames. So the frame of a swinging pendulum is a non-inertial frame. The example that follows, I hope, will make things even clearer, because on the Earth, it is hard to ignore gravity. So let's go away from the Earth. Let's go out into outer space, very far from Earth, Sun, and other objects, where to some reasonable approximation, we really are isolated. Okay, so we are in this faraway spaceship, faraway spaceship. All right, now So let me go through this carefully. For instance, a frame, so I'm going to give an example of a frame that is not inertial, where Newton's first law doesn't hold. Okay. So what is that frame? We go to this faraway spaceship. We have a bee inside that spaceship, and that bee flies around the spaceship, yeah, in some irregular manner. It has its motion. Now, suppose you have a frame that is attached to the bee. Okay, so one axis points from the center of the bee to its nose, the other one towards one wing, and the other to the other wing. Right, so you have a frame set up in the bee. Now, as the bee moves around, this frame will also rotate, twist, and so on, go around the place. Such a frame is not inertial. So let me read this carefully. For instance, a frame that is attached to a bee that flies irregularly in a faraway spaceship is not inertial. And why is it not inertial? It is because a free particle that's also in that spaceship, okay, far away from other interactions, simply at rest in that spaceship, when viewed from this bee frame, will not look like it is at rest or in uniform motion. It will look as though it is moving around very randomly. I mean, mirroring basically the motion of the bee. Okay, so a frame that is attached to a flying bee in a faraway spaceship is not inertial because a free particle at rest in that same spaceship, would appear to move in a non-uniform manner. Okay, so we have come to the first important observation that Newton's first law doesn't hold in all frames. We have to restrict to a certain class of frames, and it's only in those frames that it holds. Yeah. So in the case of the spaceship, a frame that is fixed in the spaceship would be an inertial frame. So a ball that is at rest in the spaceship would appear to be at rest. It would not move. Okay, so that would be an example of an inertial frame. But then suppose instead you consider a frame that is attached to a top. Okay, so here's my top. Yeah, this is my top and it is spinning. So suppose you have a frame that is attached to this top, then that frame would itself be spinning round and round. And when you look at the world from that frame, a particle at rest in that spaceship would look like as though it's going round and round, certainly not at rest or moving uniformly. So we say that a frame that is attached to a top and participates in the rotational motion of the top is not inertial. Okay, because free particles would not follow straight lines when viewed from that frame.
Sir?
Yes, Shubham Kumar,
Sir,
yes.
Sir, we are saying that the top is rotating with when we are seeing it from the inertial reference frame, right?
Yeah, so very correct. So let us think of the Earth, and I have a top on the Earth. Now we have come to the observation that the Earth is an inertial frame. Okay, we will now accept that. That is, on the Earth, to reasonable approximation, particles that are not subject to other forces like gravity and friction will basically travel in straight lines. Now, this has to be checked. Okay? When I say this is an inertial frame, you have to check it. You have to bring a free particle, keep it in that frame, or situate it relative to that frame, and check, does it move in a straight line or not? Okay, so this is an experimental question. Suppose we have checked that the Earth is an inertial frame. So we are now in agreement on that, having checked some experiments. Having done that, we now consider a new frame, namely a frame of a spinning top. That is, I situate myself on a top, go round and round with the top, and see the world from that top. That frame, I claim, is not inertial because particles that I have already confirmed are at rest or are moving at straight lines in uniform speed relative to the Earth would be seen to be spinning, would not be seen to be at rest. Okay. So is that clear to you, Shubham?
Yes, sir.
Okay, very good. Now, I must say that this concept of Newton's first law is far from obvious. It is not an assumption, it is a law of nature. And it took a very long time to even come to this understanding. So I encourage you to think about it, reread what we have been speaking about, and try to clarify things for yourself. I will add a few more remarks now, which I hope will help.
So could you please repeat the last point again?
The last point. Okay. So the last point, based on the question from Shubham, is that first, what do? We check that Earth, when I say Earth, a frame fixed on the Earth. Yeah. That frame fixed to Earth is inertial. What does that mean? Okay, I fix that frame. This is the frame because I am sitting on the Earth. I am fixed. This frame is also fixed. And what must I do? I must conjure up particles which are free, which don't feel the forces of gravity or other frictional force with air and so on. I must observe their motion and observe that they travel in straight lines at uniform speed. If that is true, we will come to the conclusion that the Earth is an inertial frame. And this must be true for all particles. You must check all particles. All right. I mean, that are isolated. Having checked that a frame is inertial, now I was using the Earth as an example. You can take the frame of the spaceship also. Yeah. Suppose I'm sitting in a spaceship far away from everything else. I think that makes it more plausible. So let us frame fixed to spaceship. Far away spaceship. Yeah, suppose we have checked that a frame fixed in a faraway spaceship is inertial. Now, in that spaceship, I put a little top, a toy top that is spinning, and now I fix my frame to that top. So as the top rotates, the frame itself will rotate along with the top. Now I watch things from that frame. I watch a particle that is at rest in the spaceship from this rotating frame. When I do that, I will not observe that particle to be at rest anymore. It will be as though that particle is going round and round me, and not in a straight line either. All right, be executing some kind of circular motion.
So what if we stand at the axis of rotation of that toy, then like we want to be rotated?
No. Look, a frame consists of 3 axes. You can align one of the axes with the axis of the top, but the other 2 are still going to go round and round. All right. So, and suppose I situate myself along the axis of the top and look out. At one moment, I'm going to see this camera. At another moment, I'm going to see this wall. All right. So if a particle is fixed on my screen, it's not going to look fixed to me anymore. When I turn around, it's going to move towards my left and so on. So,
no, sir.
So
yeah. Supposing like your feet are particle object, then like you won't like rotate with the whole toy also.
Okay, no. I was giving an example of a non-inertial frame. There are lots of inertial frames. Yeah, I mean, I didn't quite understand your question. Could you repeat it?
So like the toy is rotating, but like considering human body as a non-thickness road, and like then the road is situated on the axis of rotation, then like it won't rotate with the toy.
No. I am talking about a frame. A frame is not some zero thickness object. A frame consists of 3 pointing axes of this sort. Yeah. So there is no sense in which, and if it participates in the motion of the top, then it's keeping on rotating. So we cannot approximate a frame by an infinitely thin rod. That would not be a frame. You need 3 axes to define a frame.
Frame is not a like practical thing. It is just a notion that we define.
It is both. I mean, I am showing you a frame. It's in my hand. This is the frame. Yeah, so it is a very practical thing. It is more than just a notion. I mean, it's a set of 3 wires emanating from some place. So it's very real. And we can ask the question, is that frame rotating relative to the spaceship or is it not? This is a question that can be answered. you are free to imagine frames that are hard to construct, sure, but that doesn't mean they are not, they do not have a reality in the sense I am describing.
So I think what Shakti was trying to consider was a free particle that was on the axis of rotation on the top. So then even because it's a point particle, even if the top was spinning and the frame was spinning, the particle would look to be.
Very good. Excellent point. Yeah. Okay. So if that was what Shakti was asking, Romit Roy Chaudhary has introduced an important question. Now, for a frame to be inertial, it's not enough that one particle that you pick happens to be, which is free, happens to lie along a straight line trajectory. Every particle must have that property. So yes, you picked a particle that happened to be on the axis of the top and therefore looked as though it is at rest. But I will pick a particle that is not on the axis of the top and it won't look like it is rest. So that brings me to my summary. So sorry, Romit, does that clarify?
Yes, I'm fine with it.
Yeah, okay, you are fine with it. So let me, but you do make a very good point, and that is what the summary statement here is supposed to do. To summarize, Newton's first law is the assertion that there is a frame of reference called an inertial frame in which this word is very important, in which all isolated bodies, namely those that are far from physical interactions, move at constant velocity. Okay, so it is not enough to check it for one particle. I have to keep on checking it for all particles. If this statement fails for any one particle, then that frame is not inertial. All right, of course, we check it for a reasonable collection of particles and we then work with that in practice. Now, a couple of remarks. Henceforth, unless otherwise stated, all quantities will be specified with respect to an inertial frame of reference. Okay, to make our life simple, we will, at least in the initial part of this course, deal with physics as viewed from inertial frames. When I say inertial frame, I mean a frame in which Newton's first law holds, namely a frame in which isolated particles travel in straight lines at constant speed. Okay, so that is the definition of an inertial frame, and we will view physics from an inertial frame. Later on, we will talk about non-inertial frames as well. Now, one more remark. I said it is the assertion that there is a frame in which all isolated bodies move at constant velocity. You may immediately ask, now, is that frame unique? Answer is no, as we will see shortly. From a principle enunciated by Galileo, an inertial frame is not unique. Okay, so if you have found one inertial frame, there are others as well. There are infinitely many, and we will talk about how they may be obtained. I mean, it's not hard to imagine. If this is an inertial frame, then so is this. Okay, I mean, they are not moving relative to each other. If things look at rest in this frame, they will look at rest in this frame as well. Okay, or if things look as though they are in straight line motion uniformly in this frame, so will they look in that. All right, so inertial frames are not unique by any stretch of imagination. Okay, so this is our discussion of Newton's first law, and we are now basically out of time for today's lecture. So we shall meet next on Thursday and continue our discussion. Any urgent questions before that? Okay, Romit had a question or no?
Okay,
please ask.
Yeah. So I wanted to ask that when we are saying that a body is at rest or moving with constant velocity, with respect to which frame are we saying that are we assuming that Earth is an inertial frame, like at the beginning?
Then it's relative to the frame fixed on the Earth. Yeah. So okay, let's state the question, the sentence clearly. We say that a frame is inertial, so that means we already picked the frame. We have specified the frame, so we have to say which frame. I mean, a frame fixed to my table, yeah, in this manner, yeah, or a frame fixed to my head in this manner. We have to be very clear, or a frame fixed to a spaceship. Yeah, so we have to say which frame, and then in that frame we are asking the question, how do particles move? If by doing experiments we find that particles always move in straight line with uniform velocity, then we will declare that that frame was inertial. Does that help, Akash Yadav? Is that Akash Yadav?
Yes, sir. I mean, like if we are considering the spaceship and the Earth, like if we watch from the Earth, the particle in the spaceship, so that would be moving, right? Because
Yes.
the Earth. Yeah.
Correct. So from for such considerations, the Earth is not an inertial frame. Indeed, you're quite right. The Earth is not an inertial frame because it is rotating and going around the sun and all sorts of things. So for many purposes, the Earth is not an inertial frame. However, for certain purposes, it is an inertial frame. For the motion of tennis balls on the Earth, it is very much an inertial frame to good approximation. Yeah, but it is not. If you want to view something very far away, no, the motion of the Earth becomes very important.
Okay, sir. Yeah.
Yeah.
Thank you.
Any other question?
Sir, like it's like in the
Ruptak Majumdar. Yes, please.
Yes, like in the statement of the first law, like it was said like far from like a physical interaction and stuff. What does that exactly mean?
Okay. This is not okay. See, we can say it through examples. All right. And what I said was that you simply go far away from the sun, earth, moon, and other celestial objects. And that is a reasonable way of looking for isolation. Yeah, I mean, there are ways of measuring how much, how far away you are, or but I agree with you that this is a somewhat imprecise concept. It is an idealized concept, and okay, the way to understand it is to, for instance, we will assume that the Earth is inertial, yeah, and observe certain motions, say of pendula and so on. Now, it may be that we will find that there are some small effects which we can measure or calculate, showing the non-inertiality. Okay, so that way we will be able to quantify this departure. Okay, my statement was somewhat cryptic, I think, to you. Maybe later on, when we talk about non-inertial frames, things will get a little bit clearer. But for now, I want to just say that by going far away from other physical objects, you become isolated. That's about it. We are not being particularly more precise about it. The farther away you get, the better this approximation would be. That's about it.
Yes, sir. Thank you, sir.
Yeah.
So,
yes,
so can we, Sir Amrapunjan?
Okay,
so
yes,
can
please.
we think of this in this way, that say there is a force, like it is like, because if any two bodies will interact, there will be some acceleration. So because if there is acceleration, you will have to subtract the relative acceleration, which is like a pseudo force will act. So an inertial frame should be one where no force acts on the object,
okay,
so that you have no form of it.
Yeah, now I think you're getting a little ahead of ourselves. See, isolated simply means, see, okay, it is an observation that interactions between objects, bodies, tends to decrease with distance. This is a practical observation, that we feel less pull towards the Earth if we are a little farther up than we are closer to the Earth. This is a experimental observation, and we simply stretch that further and further to define what we mean by an isolated body. Yeah, I wouldn't. Okay, yes, there are matters concerning pseudo forces and so on, but I don't think that is needed to explain what an isolated body is.
So the reason that I told it in this way is, so consider a universe where there is a constant force acting on like a same amount of force acting on every single body, So if there are 100 bodies, a same amount of force is acting on each of them, so that no relative velocity can change, because like no relative position change, or there is no change in any dynamical variable because of that force. So in that case, the definition of inertial frame, that every single object should obey the force law, will hold. But even then, there is some interaction that is coming from outside. So if like there is some god who is pushing the entire universe, so in that case, will it be like inertial or non-inertial?
No, wait, see, to talk about, wait a minute. Okay, I need to understand your example more carefully, but may I first say that in practice, there are no forces that are so long range that are constant across the universe. Okay,
Yes, sir. I'm asking like in principle, like in theory, not in like.
Yeah. So if there were such forces present, then it would be very difficult to define what one even means by an inertial frame. If you cannot isolate a body, then how can you check that isolated bodies travel in straight lines? So then Newton's first law would not be particularly useful. Yeah, or you will have to somehow artificially cancel out that force so that the body is approximately isolated, and then check Newton's first law. Yeah, so that's the point. I mean, Newton's first law is an assertion about free particles. It's about isolated bodies. So if you don't have isolated bodies, or you cannot isolate a body, then Newton's first law is not a particularly useful concept. Sorry, please go ahead.
Yes, sir. So like, for example, like if we consider the surface of Earth, very close to the surface of Earth, and we assume that this is our entire universe. So in this case, we assume the Earth's gravity to be constant. So if this kind of a constant force is acting on every object, then I won't be able, like, even I'll be accelerating with the same acceleration as any other body. So like Newton's first law will hold in my frame if there is no other force other than this constant force of Earth. So in that frame, will I be an inertial frame if there is something like
that
this
is not
happening?
an inertial frame, because I mean, if you are saying that there is a force of gravity acting and it's constant, then particles are
Sir, I'm
simply
just
not
giving an
free.
example.
No, no, that
So I'm
frame
just
is not
giving an
inertial, because no. See, if you're okay, all right. I would suggest. See, if you can in some way ignore that force, cancel it out, or do something to get rid of that force,
Yes.
then we can talk about isolated bodies. And then in that frame, so the Earth is, to reasonable approximation, an inertial frame. And it is true that there is a gravitational force here, but there are bodies which simply don't feel the gravitational force. Suppose we work with such bodies, yeah, then they feel as though they are isolated. And then in such in such cases, one can check, do they travel in straight lines or not? Yeah, or you somehow account for the effect of gravity and then subtract that off, and then see, are isolated bodies traveling in straight lines? If that is the case, then you will conclude this frame is inertial. I mean, in practice, that is what you would need to do.
Sir, like, can I, sir, mail this to you by like properly expressing it in words, like exactly what I'm trying to say?
Okay,
sir, I'll
sure.
mail it.
Yeah.
So I think he's asking, like, suppose there is a frame and there is a particle isolated from every other system, and there is a single force acting on both the particle and the frame. Then the frame would be inertial because both of them will have the equal acceleration.
See, look, I think these are all questions that need to be asked at a later stage when we talk about accelerated frames. I'm not sure. Okay, perhaps we will try to address it at a later stage, which I do plan to do. I do plan to talk about accelerated frames later on, where there is a uniform gravitational force or an acceleration, uniform acceleration. So at that stage, these ideas will become more clear. Yeah, right now, when I talk about Newton's first law, we have to have some way of isolating a particle and asking whether the isolated particles travel in straight lines to lead in a reasonable approximation. That is what an inertial frame is. We have to have some way of ignoring the forces that are present, canceling them out, or something has to be done to answer the question, is this an inertial frame or not? Yeah, any other question? Okay, so
Sir, in the
All right.
case of isolated bodies, what if the body possesses some internal force, like
I'm sorry, please say that again.
so when we talk about the isolated body, what if the body have its own internal force, like no force acting from outside, but its own, like suppose there is a bee
Yeah.
flying, then it would have its own muscular or like its own energy.
Right. Sure. Okay, look, I had a that should not affect things very much. All right. I mean, I'm thinking of a bee as a very small object, and yes, there may be some internal forces holding the bee together, but I'm thinking of the bee as basically some kind of rigid object, and it is flying around. That should not affect things. No, the fact that there are internal forces holding the bee together are just help us to make the bee. The fact that the bee is flying in an irregular way is the more important matter, and that we have a frame fixed to the bee is really the important thing.
To move irregularly, it must possess some acceleration. If it is possessing acceleration, then there must be some force acting on it, sir, either internal or external.
Sure, in this case it's internal. It has had a good lunch and it's able to move around. That's all. Yeah, see, we are not concerned with how the bee moves, and if you don't like a bee, we just, as you said earlier, we can hypothetically make a frame in the spaceship that moves in this jagged way. All right, that's it. No bee is present. We just imagine a frame that moves in this crazy way, and we observe a fixed particle in the corner of the spaceship from that frame. Yeah, so if you like, look at it that way. But the fact that the bee has got an internal structure or has had a good lunch and is able to move around, it doesn't affect these conclusions. The fact that the bee's frame is non-inertial is a conclusion independent of how the bee moves.
And also, sir, from the frame of reference of the object that is lying in a corner in the spaceship, that B is still like accelerated motion, but the frame is itself inertial. So
yeah, okay, no, there you are right. So the B is able to do certain things. So B is somehow not a free particle. That's quite right. So when I view the B from the frame of the frame fixed in the spaceship, I cannot, it is not true that the B is a free particle. The B is got some engine inside it, and it's able to do things that free particles can't do. Yes, you are right about that. Perhaps my talking about a bee has caused some unnecessary confusion. Yes, a bee in a spaceship is not a free particle.
yes, sir. Yeah. Thank you, sir.
Yeah. Oh, okay. Any other questions? All right. Anyway, thanks for your interest and excellent questions. We shall continue the discussion of Newton's laws next time. For now, I wish you a good afternoon. Let us stop this lecture here. Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yes.